David likes books. He only ever pays 99p or £1.99 for an electronic book. In the last few months, he's spent £56.56 on these books. How many costing £1.99 has he bought in that time? So I'm going to say that he's bought X electronic books at a 99p, which means the total cost will be 99x. And then Y, that would be £1.99. So that's 199 pence. So the total cost would be 199y. And if I add those two together, that's going to give me 5656. What I've created is what we call a Diophantine equation. Two unknowns, but they have to be whole numbers, in fact, positive in this case. And the normal strategy is to try and find any common factors, but there's a problem here because 9 and 11 go into these, at 1, 3 of course. 199, however, is prime, and then 5656 is actually 56 times 101, so 7 times 8 times 101. So actually they don't share any common factors, and we're left to try and deal with this some other way. It's got to be said, in the middle of a maths challenge, when you're under time pressure and if you can't quite see a method straight away, I'd be very tempted to just try out the answers until we get one that works. So I'm going to talk about it that way, and then we'll talk about a method where we could do it without the multiple choice, because that also is very important in our development of maths. Imagine we get onto harder maths, Olympiad problems and so on, then you won't be given a multiple choice to kind of just put it back in. And you don't really want to be trying every single value. Okay, you could systematically work your way up and figure it out, but there's got to be better methods, and there is one here. So if you put 8 in, oh yeah, this is it would be y that we're actually replacing by these numbers. If you put 8 in, it doesn't quite work, but if you put 13 in, it does. So what we could do is 199 times 13. Basically, we're trying to get x as a whole number, and then we know that that is a solution and probably the only solution because of the multiple choice scenario. So I could do 200 times 13, which is quite quick to do, and then just minus a 13 from it. That's 2,600 minus 13, 2587 for this here. So then 99x would be 5656 minus 2587. Do a little subtraction. So 9603. And then I can do 99 into 3069. Okay, well, 99 times table is 99, 198, 297. So that's going to be the one that goes here. Remainder 9. So I can see I'm going to get 31 for x. This is a whole number, and therefore it must work out. The answer is going to be B. If you tried 15, 17, 23, you wouldn't get a whole number. And that's one way of doing this question. Let's take a look at a more sophisticated way of doing this question. This is where it's at, really. So it's all about the exact nature of this problem, the fact that both of these are one less than a multiple of 100. So every time we buy a book, let's say we buy 99p one, then it'd be 100 minus 1. And then if I buy another one, it'd be 200 minus 2. Every time I'm buying a book, we're going up in the hundreds, but we're going down by 1 in the units, essentially. If I then buy the 199 one, it would be 397. It still applies, and we could keep going. So what you can see is after we bought 4 books, we're 4 less than a multiple of 100. 5 books, we're 5 less than a multiple of 100. And finally, if I add 199 on again, it'd be 794. 6 books were 6 less than a multiple of 100. And that's what gives this question away, because here we are 44 less than a multiple of 100. So I guess we could have bought 144 books, but we can see that's going to be too big because that'll be hundreds of pounds. So it must be that David must have bought 44 books. Okay, that's not obvious, but I hope that makes sense. My little argument here that we're just going down by 1 every time, and we are 44 lower than 5,700. That must be the case. So what that means is x plus y is 44. And then There's a couple ways you could do the next bit. You could, and this is how I did it, you could just sub it. Remember, we want to find out what y is. So I could sub in for x. X is 44 minus y. So I'm going to show you this way to start with. 99 times 44 minus y. I'm subbing into this first equation. Plus 199y is 5656. Okay, I've got to do 99 times 44. Well, that's going to be 100 times 44, which is 4,400. And then I've got 1 less 44. So I'll just write it like that for the moment. Then minus 99y plus 199y is 5656. That means that 100y, okay, this is going to become 4356. And I can minus that from 5656 to give me 1300. Divide through by 100 and we get 13 using this algebraic approach rather than our guessing. So that's pretty nice. Now, if you can spot it, there's an even nicer way. I did not spot it, I got to say. So we've got x plus y equals, what was that? Already forgotten, 44. And then remember it was 99x plus 199y is 5656. Now, if you actually add them together, we'll get 100x plus 200y is 5700. Just works out lovely because now we can divide through by 100 and get x plus 2y is 57. And this probably argues slightly simpler to solve than what I did over here with my substitution. We've got x plus y is 44. We've got x plus 2y is 57. I can do the bottom one minus the top one, which is going to give y equals 13. I just do 2y minus y to give me y. X minus x, which cancels 57 minus 44, which is 13. So I've gone into this question in quite a lot of detail. You might just be someone who's like, I'm just going to sub it in, but please do take on board what I've said. I mean, I think I've learned something from this question by looking at the solutions. Even a difficult Diophantine equation where you can't just divide by a common factor, which can really help. We can use other approaches that are nice and logical rather than just trying out values until it works. Anyway, well done.